Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 31. It's on the magnetic force. Imagine we have a charged particle, like a proton, moving through space. Since there's no force acting on it, no field acting on it, it's just going to keep going in that direction. But if we have a charged particle that's moving by a magnetic field, like it's rushing from the sun and it's coming by the Earth, and the Earth acts as a big magnet, what it's going to do is it's going to apply a force to that, and it's going to spiral into the planet, and it causes the northern lights. As these protons and electrons hit in our atmosphere, we're giving off ionization colors. And so as we move into magnetic forces, we really are moving into a third dimension. And so we have to have a way to deal with that. So if we have just two dimensions, it's easy to do that on a piece of paper, but how do you do it with three dimensions? A magnetic field, for example, coming at you or going away from you. The way I remember it is it's like an arrow. If an arrow is going through a hole, you're just going to see that point on the end. And so if you see concentric circles like that, or a bunch of them, that means the magnetic field is coming towards you. And then the tail end of the arrow is going to look like that. And so if we see a plus sign or a X inside the circle, that means that it's going away from us. And that'll make sense when you see diagrams like this. So we've got a magnetic field you can see that's coming out at us. And let's say we have a charged particle that has no velocity. It's just sitting there. Is there a magnetic force acting on that charged particle? The answer is no. If it's not moving, there's no magnetic force. But as it moves, it has a velocity vector. And if you're ever moving as a charged particle through a magnetic field, then you're going to have a force applied to you, and we call that the magnetic force, or F sub m. Now, things that you need to remember is that it's a perpendicular line between the magnetic force and the velocity, and it's also perpendicular between the magnetic force and the magnetic field. But the velocity vector and the magnetic field vector don't have to be perpendicular to each other. How do we calculate the magnetic force? Well, there are only three things that really deal with that. First one is going to be Q. That's going to be the charge of that particle. In this case, it would just be the elementary charge. We then have the velocity vector, or the speed of the particle, and then we're going to cross product that with the magnetic field. And what's a cross product? Well, these two vectors, when we multiply those together, we're going to get a third vector that's going to move in a different dimension. And I got an animation that's going to show you that. Now, depending on that angle, we can get different amounts of this magnetic force. And so we use sine theta to figure out how much that's going to vary over time. And so let's say we have a magnetic field like this. You can see that it's coming at us. To figure out where that magnetic force is acting, you have to use the right-hand rule. And so it takes a second to get this figured out, but I'm going to hold my fingers out like this. So I've got my index finger pointed out. That's going to be the vector of the velocity. So in other words, where that charged particle is moving. I then have my middle finger moving at 90 degrees to that, and that's going to be the magnetic field. And then the force is going to be your thumb. And so you try to make these three dimensions with your finger, and you can solve really intense problems like this. You might look like an idiot as you're doing that, but it's worth it. And so let's say we have a charged particle that has no velocity and it's in this magnetic field. How big is our force going to be? Well, we're not going to have a force. Again, if it's not moving, there's no force. And so let me give you a harder problem. Let's say we have a magnetic field like this, and we have a charged particle, a positive particle that's moving up and to the left. And so how do you figure out where that magnetic force is going to be? Well, first of all, make your hand like this, and then you're going to point your index finger in the direction of that moving charge. So I'm moving it up and to the left. Then you want to make sure that your middle finger, that magnetic field, is pointed towards you, because you can see on this diagram that the field is coming towards us. And so once I've got that in order, my thumb is going to show me the magnetic force. And so that's going to go up and to the right. So that was pretty easy to solve. Let's go to another one. Now we've got a different magnetic field, and let's say that that charged particle, that proton, is moving from right to left. How do you solve this one? Again, stick your finger towards the left. That's the movement of the particle. Now the magnetic field is not coming towards you. It's going away from you. So I have to turn my hand like this. And now where's the magnetic force? Well, you can see that that's going to be acting down. What if we have one like this? So we've got a different magnetic field. What if we have an electron moving? Okay, so if you have an electron moving, there's two ways you can go at this. Number one, you could just use your right hand and then just turn the force around when you're done, or you've got a left hand, and the left hand's going to work great. So I'm going to put point my index finger in the direction of the movement of the electron. The magnetic field, my middle finger, in this case, is going to come at me. And so where's the force? Now the force is going to be to the left. And so if you know the magnetic field and you know the direction, you can always figure out where that magnetic force is going to be. Now the angle, as I said, is between the velocity and the magnetic field is not always 90 degrees. And so we call that theta. And depending on what that is, we're going to get a different amount of that magnetic force. And so those two are perpendicular, but the third one is not going to be perpendicular. And so here's our equation. It's a little scary, but it's not that bad. Q is going to be the charge, V is going to be the velocity, and then this is a cross product between the two. And so let's watch the animation before we get to the sign of theta. And so if they're pointed in the same direction, velocity and magnetic field, we have no force. But watch what happens when they become perpendicular. We have a greater force, or magnetic force. If it moves to 180 degrees, what's our magnetic force at this point? It's going to be 0. As I move it back to 90 degrees, then it's going to be at its maximum at this time. And so by using this sine theta in the middle, we can figure out how much this cross product, or in other words, multiplying the velocity times the magnetic field, is affecting the overall magnetic force. And so the parts of this formula are Q, which is charge, measured in coulombs. V is going to be the vector velocity. That's going to be in meters per second. And then we have B, which is going to be our magnetic field. And we measure that in Teslas. And then as we solve for the magnetic force, that's going to be measured in newtons. And so let's get to that theta and the sine of theta. Where's that coming from? Well, let's say that our magnetic field and our velocity are perpendicular to each other. We know that that's going to be the maximum amount of magnetic force that we can get. What if it's this direction? They're in opposite directions. Do you remember what our magnetic force is going to be here? It's 0. And if they're both moving in the same direction, it's also going to be at 0. And so if we just choose that angle to be theta, and then we have sine of theta, look what numbers we're going to get. So if it's a 0-degree angle, sine of 0 is going to be 0. There's going to be no magnetic force. Likewise, sine of 180 is going to be 0. But if we're at 90 degrees, that's going to be 1. And the AP folks say that you should really understand 0, 90 degrees, and 180. But the sine makes sense to me, and it should make sense to you as well. What's our angle look like right here? Well, that's around a 45-degree angle. So what's the sine of 45? It's just going to be 0.70. It's going to be somewhere between 1 and 0. And so if we do a problem like this, calculate the magnetic force acting on a proton traveling at 3.0 times 10 to the 5th meters per second, perpendicular to 0.32 Tesla magnetic field, how could you figure out the magnetic force? Well, you just start with your equation, QV sine theta of B. What do I know? Well, I know the magnetic field, that's 0.32 Teslas. I know the velocity, 3.0 times 10 to the 5th. I know what the sine of theta is going to be because that's a 90-degree angle, so that's going to be 1. The only thing I don't have, it seems like, is Q. That's going to be the elementary charge. So we just write that out like this, and then we solve, and we're going to have a really small force that's acting on that charged particle, that proton. And so did you learn to apply mathematical routines to express the force exerted on a moving charged particle in a magnetic field? Always use your right hand, and you'll probably need a calculator to do the rest, and I hope that was helpful.